So our presentation is on carbon dioxide filtering, and carbon dioxide filtering is the process of converting carbon dioxide to oxygen. There are multiple ways of doing this, into which we'll go later, but we're using the activated carbon method, this is activated carbon. We're not using it in this form, but essentially it's the kind of carbon you take when you have a stomachache. And we'll be using this carbon to react with carbon dioxide and to release oxygen. And we'll be doing so in an aquatic environment as opposed to an air environment, just because of the pure simplicity of this method. It just turned out to be that way. So, as I said earlier in the previous slide, there are 5 ways to chemically filter carbon and release oxygen from carbon dioxide. There's amine scrubbing, which is used in power plants, not only to filter out carbon, but other impurities to the air, such as sulfur. There's a mineral method, which uses a mineral filter using various different minerals that will bond with the carbon and release the oxygen. Sodium hydroxide method, which is the same as the activated carbon method, but using sodium hydroxide. The lithium oxide method, which is putting masses of lithium oxide into an air filter, heating that air filter, and pumping air through it, upon which the carbon will react with the lithium and release the oxygen. And there's the activated carbon method. However, we decided to use the activated carbon method because it was the most simple to do and it was guaranteed to give us results, as opposed to in many of these other methods there wouldn't be an apparatus that would be sufficiently small enough for us to use or possible for us to construct because of various limitations. And so, as I repeated earlier, the carbon dioxide is absorbed by the activated carbon. The activated carbon bonds with the carbon, and when this comes out through the other end of a filter, we get oxygen. And this works both in an aerial environment and in an aquatic environment. And so we'll be using this process using an activated carbon chemical water filter, which uses the above described process to filter out carbon dioxide out of water. So on the other hand, we have a biological filter. And this filter comes in the form of a plant, and it will be using the process of photosynthesis to change carbon dioxide and water and we're using sunlight energy into glucose and oxygen and a little bit of water. And so this process is the alternative to the chemical process, and it's cheaper, and it works both in an aerial and aquatic environment. And we will be investigating which one of these two, the activated carbon method using a chemical filter or a plant using photosynthesis, which one is more effective for removing carbon dioxide from water. So the plant we're using is Hygrophila carambosa. It's native to Southeast Asia. It's really fast growing, so that guarantees it'll be photosynthesizing at a significant rate. It prefers high nutrient water, which means that various impurities that might be contained by our water will not harm it seriously. And it benefits from additional carbon dioxide, which again guarantees that we'll have a significant photosynthesis rate. And this plant is definitely suited for this task. This image describes how our chemical filter works. This is a gas mask. It also uses activated carbon, and our water filter is almost exactly the same, except for it lacks an aerosol filter. So again, we're using this in an aqueous environment. So we'll have our water coming in the filter, of course without the aerosol filter, and it'll be coming through the activated carbon, where the carbon and the carbon dioxide will react with the charcoal dust or activated carbon, and the only thing that will come through the other end of the filter is oxygen. So to investigate in this experiment, we chose this following apparatus. We chose two pH probes. pH changes based on the amount of carbon dioxide contained in the water. So carbon influences the pH in the following way. So it's the less carbon there is contained in the water, the higher the pH will be and the more acidic the water will be, or the more carbon dioxide and the more basic the water will be. And both extremes, they're not particularly helpful for the growth of plants, but we will be oversaturating the water with carbon dioxide just to see a significant reaction. So we have our two pH probes, we have a Vernier Mark II data logger, which will be graphing our experiment as it goes. We have two 5-liter water jugs. In one we will place the plant, and in the other we will place our chemical filter. So we got our chemical filter, and in the other we got our plant. And both of them are filled with water, and each of them have a pH probe in them. And the pH probes are connected to a data logger, which will give us a graph. And we have one 250 milliliter graduated cylinder in order to measure out the exact same amount of water. Then we used, so in order to saturate our water with extra carbon dioxide, we'll be dissolving hydrogen bicarbonate into this water. And we made sure that that amount wouldn't kill the plants by simple hypertonic potential, and we'll be using exactly 184.79 grams of that, and we have checked that amount is soluble in the amount of water we have and it won't kill the plant. To measure that out, we'll use a weight that is accurate to 0.01 gram, and we have 11 buds of Hygrophila carambosa siamesis on one end for our biological filter, and on the other end we have our activated carbon filter. So to perform this experiment, we fill our 5-liter jugs with 3.25 liters of water each. We measure out on the accurate balance 184.79 grams of hydrogen bicarbonate in two separate watch glasses, and we mix them with a glass rod into their containers until they're fully dissolved. Then we insert our pH probes into the data logger and calibrate them. We set them up in clamp stands and insert them into the jugs. So we insert them into the jugs, and only after that do we insert the carbon dioxide filter in the activated carbon filter into one of the jugs and the plants into the other. After that, we start the data logger, and our experiment starts and goes for 20 hours. So these are results. As you can see, they're graphed, and we have a slope on each of them. The lower result is the plant, and the upper result is our activated carbon filter. And as you can see, the water in which the filter was contained had a higher pH, and the water that the plant was contained in had a more acidic pH. And what this means is the plant removed more carbon dioxide from the water than did the filter. And also, as you probably can see, we have fluctuations in each of our readings, and there are two reasons why these might have occurred. For the plant, it's because it takes time for the plant to it takes in the carbon dioxide from its water surroundings in like a cyclic process. And also, both of the pH probes, hydrogen ions build up on the sensor and then slip away in like periodic cycles. So as you can see, these little dips, that's what they're accounted for. And because of this cyclic like up and down behavior, we decided to use a slope. And here I will highlight our slope right there. And as you can see, they're not especially different. But, however, the plant still remains a viable option, and We will discuss the reasons for it being a viable option in the next slide.